Today we're delighted to have Seth Sanders here, coming to us from Duke. Seth is an economist, and he works on a number of very interesting things in economic demography, including poverty, mortality, fertility, migration. I guess a common thread is that he likes to work empirically. He likes to work on inequality. And today he's going to be presenting work on mortality. One of the reasons that I wanted Seth to come right now is that he is coordinating a large project on microdata from US microdata from the 19th and 20th century, which I don't think he's going to be talking about much today.
It's kind of the precursors.
But this is the precursor to that. So what's going to happen is that all of the census microdata is going to be get individual ID numbers, and it's going to be linked to mortality data and earnings data and all this kind of thing. So Seth is kind of at the forefront of putting this project, which is going to take place over the next 10 years. So thank you for coming. Our format is that we will probably interrupt you as you go, and we'll try to get you to stop a couple minutes before 1 so we can take the final 10 minutes or so of questions.
Sure. Thanks. Yeah, and I'd be glad to talk about this large project that we're doing with the Census Bureau, which is really fabulous. I mean, like we wrote a grant, and the first line of the grant is that we wanted to link 1 billion records over 150,000 years to study intergenerational mobility. That's pretty big. I'm a little dumb.
Can people hear in the back with the heat on? Louder, we have the heat on.
Oh, the heat's on. Okay. So today I'm gonna. This is related in the following sense. I've been working now for 7 or so years, maybe longer, on using matched data sets. That's really what I've been working on. And this is an example of a matched data set that I'm going to talk about, a couple matched data sets that I'm going to talk about. And let me give you a little bit, because this paper's never been presented before. So I want to tell you a little bit about the status of the paper, because when I say we're really looking for feedback, we really are looking for feedback. This is a good story about the review process. So we put together a very small paper, like almost a note to demography on black-white crossover, making a very simple point from one matched data set that we had constructed. And we got back the referee reports, and and one of the referees was not very positive, and for good reason, But this has never happened to me before. The two referees said, there actually might be something to this paper, but if what you think is going on is really going on, this can't be a note. This has to be a full paper. And so they gave us a lot of things. They said, this should help explain black-white crossover, but it should help explain the Hispanic paradox, and it should help explain the deceleration in mortality rate towards older life. And if you could show us all these things were true, you really have a paper. So we said, oh, that's a good idea. And so I don't know if one of the referees is in the room. This is Berkeley, this is mortality, so it's pretty high chance. But it's one of the most positive experiences I've had in the review process, getting an extremely detailed set of comments and just following up on them systematically, and it's really, I think, made a big difference in what we're learning about estimating old age mortality. So that's where the reason there's not a paper is that it's kind of in halfway in between right now. I do have a 45-page document, but it's a little bit incoherent. So, all right, so let's see, how does the clicker work? That's like the key. No. Okay. Should I just do that? All right, so it's a little hard to face you guys. So this is Berkeley. I don't really have to go over a lot of this. There's a lot of interest in old age mortality. And so here's 3 controversies, and I'm sure you guys know probably more about this than I do, and I think the state of the literature is as I'll say in a few minutes, is that some people would consider these things facts, and some of these people, I think, would consider these things fiction. So it sort of depends on where you are in the debate. So there's been a long-term debate on whether mortality rates slow with age and whether they plateau. So some people at some points in our intellectual history, I'm not exactly sure where we are right now actually, thought that if you got old enough, that life expectancy was constant. So if you got out to age 102, you had 3 years to live, and if you made it to 105, you still had 3 years to live. If you made it to 110, you still had 3 years to live. And that's what's known as the mortality plateau, which is the hazard rate for mortality at least slows down and maybe even becomes flat at older ages. Okay. A second debate is the question about why do blacks appear to have higher mortality at younger ages, but lower mortality at older ages, and that is known as the black-white crossover. I think people here are probably intimately familiar with that. And then the other question is that Hispanics, especially given their low SES, tend to have remarkably low mortality rates, and I think that's true, especially for immigrants, and it's especially true at older ages. So for each of these controversies, as I said, there's two kinds of explanations. One are biological and social explanations for old age mortality, and the other is bad data. Okay? And this paper is decidedly about bad data, or I think more exactly what this paper is about how even very, very good data can be bad. So even very, 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 what I think we have is very, very good data, but because we're estimating something that's really, really hard to estimate, it turns out that data quality is going to be really important. And so this paper also explores how the same bad data issue can affect all three of these debates, and that's actually thanks to the referees. Okay, so let me, boy, I don't want to spend too much time on this because you guys invented this stuff. So, but I'm gonna give you my my 1 minute view of the intellectual history of mortality estimation. Okay, so like, what can you do in 1 minute? So what I would say is that a lot of earlier studies used two samples to construct mortality rates. The idea was to many studies use death rates that come from a vital statistics registry. I'm really thinking about in developed countries, not in developing countries, where vital statistics registries are pretty good. And then we have something like a census in order to get the population at risk. And a number of people, including people in this room, pointed out that there are a lot of limitations to using two samples to estimate mortality. And I think the most important that comes in various forms is that different recordings of the conditioning information between data sets makes it difficult to construct mortality estimates. Okay, so this comes in a bunch of different forms. One form is that people who are recorded as Hispanic on the census may be recorded as white in the death certificates, making the death rate for Hispanics inappropriate low and slightly high for whites. Another example of this is the famous age misreporting example. Okay, especially if we think that age is being misreported. You may find that you have people that let's see how this works. You have people who are 70 in the census, and you don't have 70-year-old deaths because they're reported as 80-year-old deaths. It's another version of the data, not lining up. And often these mortality rates are only estimated for census years, but they don't have to be. You can use repeated censuses in order to estimate mortality off the census years, and you can also use backwards and forward estimators that combine death certificate data and census data in order to get the appropriate denominator for a year between the censuses. Okay. So there's been this more recent trend because of these criticisms, and part of it, so for example, I think Irma Elo and Sam Preston had a big effect on this because of their work that shows how important age misreporting is in the debate over the black-white crossover. There's been a more recent trend to estimate mortality from longitudinal studies or from cross-sectional studies matched to death records, and I'm going to talk about the second today. So here are what are thought to be some of the advantages, and these are clearly advantages. First, the numerator and the denominator come from the same source. Okay? So you don't have this problem of having to match people up by step. And so people are classified typically based on their reports in the survey, and then you follow them until they die. In the survey, age reporting is thought to be better, especially because what you tend to do is you tend to interview people when they're, say, 60 years old, and then you wait 30 years to see if they die. We think that the age reporting is probably better measured in the survey than the death certificates. And also, one form of this is to use Social Security data, where we think that age is actually verified. Okay, because in order to qualify for Social Security, you have to provide enough data so that they can verify that you're 65 years old. Okay, so these are, of course, seen as advantages. I would argue, actually, the administrative death records are very good. I think, as I'm going to show you, very good may not be enough, but they're really quite good. And I think this is increasingly important, is that they are actually relatively cheap to produce large samples, because I'll talk a little bit more about that in a second. The way these samples are typically produced is you go get a cross-section, which has already been collected, and perhaps it was collected in 1986, and it's now 2016, so you match in the death certificate data. And if you had a sample of from the National Health Interview Survey of a couple 100,000 people over a couple-year period, all of a sudden you're able to estimate mortality models over a 30-year period that are actually relatively inexpensive to construct. So they have really it's a great advantage. Okay, so what about these linked studies? So the death records and various death records have been linked to the Health and Retirement Survey. The survey we're going to talk about that we did the linkage is the National Longitudinal Survey. It's the original Cohorts. I'll talk a little bit about that. So this is called the Old Men Study or the Mature Women Study. Okay? The PSID is another panel data set that has death certificates linked. And increasingly, there are a number of these cross-sectional data sets that are linked to death certificate data. So General Social Survey, the CPS is linked through the National Longitudinal Mortality Survey study. That's a link between a whole bunch of CPSs that go back to 1973 and link in death certificate data. NHIS is linked. And the one I'm going to use today, which many other demographers have used, is the National Health Interview Survey, which is actually a fabulous survey that goes back to the 60s and has been linked to death records starting with the 1986 NHIS and going on through 2009 NHIS. Now, the NHIS is considered by many, especially in epidemiology, to be the gold standard for studying mortality. And the reason is it's large, so it has lots of subpopulations that you're interested in. You have big enough samples to estimate mortality for Hispanics. It is population representative. It has very good mid-life health data, so you have information on smoking, you have information on the covariates that you would like, and it has enough time for people to die. So even if you sample people in their 50s or 60s, they could be up to their 90s by 2012.
Sorry, just a quick question on the detail on health in the survey. That's all self-reported, right? There is no direct.
It is, yeah. On the NHIS, it is self-reported. I actually think the people here probably know the NHIS better than I do, but I think it's a telephone survey. So NHIS, which is also linked, is an in-person survey. It's smaller.
Yes.
Okay. So I'm going to make a pitch for match data, because that's what I've been working on quite a bit. I personally think that we are getting much better at matching data. And I'll show you some examples of this in a minute to show you how much better we've become at it. Mostly, we've gotten better because our data sets that we need to uniquely identify individuals are getting better. Okay, so we now have extremely large databases with lots of details on people. So if any survey you have a bunch of information on people, there's probably another administrative data set out there which has some unique identifier on it, which has the same data elements to which you can match. It also helps that we now have very fast computing, so we can go through these data sets very rapidly to find people. But my own assessment is that at this point, most of the challenges of uniquely identifying people so that you can match into something like death certificates are legal and not technical. Even on really bad data that doesn't have like social security numbers, we can find 80 to 90% of people without a lot of effort, and with a lot of effort, 96%. It's just because there's so much data out there to verify who people are. And I said this before, I also think this is going to become increasingly important because of the increasing of the cost of longitudinal data collection. This is a relatively inexpensive way to get some of the advantages of longitudinal data collection. And so what I'm going to talk about today is I'm a big fan of this, but at the same time, I think we have to start to develop models for the limitations of match data. The technology is I think a little bit ahead of where we are in terms of estimating models. Okay. How am I doing on time? I don't have a lot of time.
You've used about 15 minutes or about 25 left.
I'm not going to spend too much time on this. I talked about these three controversies, and all I'm going to point out here is that there's literature on whether these exist or whether it's bad data. Okay, so here's an example. There are people who have worked on the mortality plateau point to non-human studies that show the mortality plateau. So this is not all about longitudinal data. Some very famous people have believed in the mortality plateau, and there are statistical models that suggest that there ought to be a plateau, which have to do with heterogeneity in the population and the most robust people surviving over their ages. Okay? And then there are also people who don't believe in plateau. I've gone over some of these, that age is exaggerated. There's also some technical issues that when you estimate a discrete time hazard model, you're implicitly assuming that the hazard rate is flat within an interval, and when you get to very old ages, it could be increasing very rapidly. And there are other technical reasons for people that say, no, the plateau doesn't exist. And this paper is going to argue a new reason, which we're going to call the Methuselah effect, which I'll define in a minute. And we think that this is maybe another reason that people are finding this slowdown in mortality at older ages. What about the black-white crossover? Again, there are these frailty reasons that have been put forth, which is specifically because high mortality of African Americans happens at earlier ages, that mortality is lower at older ages because of basically culling of the weaker parts of the population. I mentioned this Preston and Elo work that suggests that a lot of the crossover can be explained by the fact that African Americans didn't have birth certificates in the 20th century, so knowing exactly what age is was really difficult. And when they went back to actually find people in early census data and verify their ages, they actually found that a lot of people had overstated their ages, and so they were dying at younger ages than they appeared to be. And I'm going to again suggest no, it's a different. This Methuselah. And what about the Hispanic paradox? Some people think there are reasons for it. There's what's been known in the literature as the barrio effect, which is basically a network effect that people think might be particularly important for older Americans. There are reasons about diet, less smoking and drug abuse, and then poor data. Okay. And the salmon effect is the only one that I think is sort of specific to this debate, which is that there's a thought that immigrants may go home to die, which is why you see more mortality. Okay, so there are at least three big debates in the old age mortality literature. Okay, so let me define the Methuselah effect. And here's the nice thing: it's incredibly intuitive. Okay, we just thought a good name might make you remember it better, but once I show it to you, it's like incredibly intuitive. So here's what we want. We just want to estimate the hazard rate. Okay, so what's the hazard rate? The hazard rate is just going to be the number of deaths let T be age. Okay, the number of deaths at some age T, and you divide it by the number of people at risk at age T. That's what we want to estimate. And I'm going to keep track of two more numbers, which is just going to make it easier to explain, which is the stock of deaths up to T. That's all the deaths that have accumulated up to, say, age T, okay? And also the total number of people in the sample, okay? And just to keep in mind a couple things, what's the stock of deaths at age T? It's the stock of deaths at 1 year earlier, plus the number of people that died this year. Okay, that's the stock of deaths. So the number of deaths that have happened, think about a cohort, the number of deaths that have happened up to age 85 is the number of deaths that happened up to 84 plus the number of people that died at age 84. Okay? That's going to be the stock of deaths. And just as the number of deaths is counting up, the surviving population is counting down. Because that's what this NT is that the number of people that are alive at T are the number of people that were alive at T-1 minus the people who have died. Okay? And finally, the number of people, the total number of people, has to be the number of people alive plus the number of people that died. So I'm really thinking about this as a cohort. That's what the notation is going to be. Okay. So here's what I'm going to do, like I think in a minute and a half, the mystery will be over. Not much of a mystery. Okay. So I'm going to split the flow of deaths at a time or at an age, and the stock of deaths into observed deaths and unobserved deaths. And let me tell you exactly what I'm thinking. What I'm thinking is when we go to match the death certificate data, we either find it or we don't find it. Okay. And we've been assuming that when we don't find a death certificate, it's because the person's alive, but it could be that we just didn't find it. Okay, so there's two reasons that when we do this match, someone might quote look alive. One is they are alive, and that is actually the predominant number of cases when they're young. But what I'm going to show is when you get old, it could just be that we just didn't find it, and I can talk a lot about why we don't find these death certificates. Okay, so here's the flow of deaths. The flow of deaths, the number of deaths are just equal to the number of observed deaths plus the number of unobserved deaths. And the stock of deaths are going to be all the deaths that have occurred up to, say, age 85. Some of those deaths will be deaths that we've seen in death certificates, and some of them will be deaths that have occurred but we don't see in death certificates. Okay, so what I'm going to do is I'm just going to define a very simple number, which is the fraction, the probability that the death is missing. Okay, so what's going to happen at a point in time is that some number of deaths occurred at age T, and some fraction of those deaths will be missing. Which means that when you go out to say age 85, we can accumulate up all the deaths that have occurred between age 0 and age 85, and some fraction of the stock of deaths will also be missing because a fraction of the flow of deaths is missing. Okay, so you're just what's happening is that as you're adding up deaths, you're also adding up deaths that are missing. Okay? And so the way we have this set up here, which is right now we just have deaths not being a function of anything. So the expected fraction since the same fraction I actually have this T subscripted. The way to think about this right now is that 4% of deaths are missing. Okay, which means that 4% of the stock of deaths are missing.
So should we worry here that if we don't agree that the top equation implies the middle equation? Because doesn't alpha change with T?
It can, it can, and then this.
Are alpha hat and alpha the same number? Yes. You think they are in expectation?
In expectation, the way we have it set up, we think they are. Okay. I'm trying to.
Is the second equation a hope, an assumption, or is it a logical conclusion from the first equation?
Well, it's certainly true if alpha is not a function of T. Okay. Right. So if 4% of deaths are missing, then 4% of the stock of deaths are missing. I have to think a little bit about what happens if the missing rate is a function of age. It's actually the one thing we haven't programmed either, so
But it's not important, we're gonna mostly use the top one, right? The
well, all that you have to believe is that at age, all that has to be true is that at age t, some fraction of deaths are not observed. Okay, as long as it's positive, it doesn't matter. All right, so okay, so here's what our hazard rate's going to be.
I don't know, superscript R?
Superscript R is realized.
The opposite of,
So all we want to let is, you know, so every year some fraction of deaths is going to be missing, and the way we have this set up is an expectation that's going to be equal to alpha, but there could be some sampling variation from year to year. So that's what the R is. All right, so here's the observed hazard rate, and then I'm going to just tell you what the Methuselah effect is pretty straightforward. So here's what the problem is going to be. The problem is going to be pretty straightforward now, which is that you're counting too few deaths because you miss alpha of them. Okay, so the numerator is too low. And then what I'm about to show you is actually much more important, is that the denominator is too high. Okay, because what's going to happen is that you're counting the number of people you think are alive, but in fact some of those people already died. So that's the entire paper. Okay, so let's talk a little bit about the observed, just to give you a little bit of intuition, the observed versus the true hazard. So first of all, generally the missing data rates in high quality data, like the national, I'm going to show you in a minute, the National Death Index is actually a pretty high quality data set. It's actually pretty low. I mean, for whites, 3 to 4% of deaths are missing, and that may be high. That may be a little bit high. So so what I would say is that often the numerator is not too far off. Okay, you get 96% or 97% of deaths. Okay? The problem is really going to be the denominator. And so here's what's going to happen. I mean, as soon as I tell you this, I think you're going to start to get an intuition for the mortality deceleration, and I'll show you in a minute the black-white crossover. Is what's going to happen is that when you're young, most people are alive. Okay, if you start a cohort and you look at the number of people who are alive at age 5, that's most of the cohort. Okay, so the number of the number of deaths is small. Okay, so the number of people you think are alive is really very close to the number of people who are actually alive. And what happens when T gets large, you get to older ages? Well, you know what's going to go on is that now the number of survivors is small. The number of people who have died, the stock of people who have died, is large. So what's going to happen is that the number of people you think are alive is going to be much, much bigger than the number of people that are in fact alive. Okay? And when you get out to an old enough age, I don't know how old this is, but it's old enough, okay, like 97 or something like that, you're going to start to observe no deaths. And the reason you're going to start to observe no deaths is because there are in fact no people alive. Okay, you observe no deaths, there are no people alive, and notice even if alpha is really, really small, like 3 or 4%, you've now accumulated all of these deaths that you've missed. Okay? So you're going to estimate a hazard rate of 0 because you think people are alive and nobody's dying, right? When in fact, the generation is actually extinct by this time. Okay? So what this says is this form of measurement error is going to make it look like people live forever, and that's the Methuselah effect, okay? Which is as you age, your hazard rate has to fall in the presence of missing data. And now the question is it empirically important?
So, to clarify, this pertains to matching data. If you're using census data to get your denominator, then dead people are still, they're dead. Even if you don't have a...
Yeah, so that has other problems, but I think
but
that's right.
That's
And I think that, I think that one way to put it, which I think is fair, is that longitudinal analysis has been kind of reified because it has all of these good properties, like it has much less age, and so forth. It has a different form of it problems. And that's the way I report it. Yeah, exactly. Okay. Okay, so it's always present unless matching is perfect. Okay, so that's the first point. The second point is a smaller point, but actually turns out to be important as well, which is it's actually really straightforward as well, is that when you go to estimate like this is going to come up when you want to estimate differences between groups. Okay, when you go to estimate the standard error of your hazard rate, you're going to tend to think you have a lot more power than you do. And the most important reason is that you think you have a bigger sample than you do. Okay, so when you get out to old enough ages, you think you have lots of people alive, and so you're doing a really good job getting the hazard rate right, but in fact you have nobody alive, or very small people alive, and so your standard errors are going to go up too. Now it depends a little bit on whether the hazard rate is less than 0.5 or not, but at most ages, life expectancy is greater than 2 years at most ages. So in general, we think that in the presence of this Methuselah effect, right, you're going to way overstate your power for picking up the differences. All right, this slide's a mess, but all it says is I just did this for a single population. I can talk about black-white differences or Hispanic-white differences. Now the difference in the true hazard rate and the difference in the estimated hazard rate is going to be a function of the difference between the rates missing data from the two groups. And what I'm going to show you, which I think is probably not surprising, is that minority groups have much higher matching error than non-Hispanic whites. And I think there's a lot of reasons for it. One of the reasons for Hispanics, I personally think, is that the American data system is not really set up to handle Hispanic names. So, if half the people in the data, half the women in the data, their names are Maria, but of course they don't use Maria, but that's their official name. So when you go to match, there are a lot of Maria Gomez's, and it's very hard to do that kind of match. Okay, so part of it's that, and part of it is missing Social Security numbers. Okay, so this is just a little simulation to see, then I'm going to get to some real data.
Before you start, just to follow up on Carl's question, if we did a different kind of match from the living to the alive or dead, and we said we did the other way around, you just started with the death records and matched backwards, do you solve the problem, or do you just create the opposite problem?
No, I think it depends, right? I think you solve the problem in the sense that if you get cohorts that are extinct, you don't have this problem. Okay, so one way to solve this problem, and this is what I'm going to show you, is that instead, if you happen to be working on a cohort that when you go to the match the data would be 115, okay, then with one very simple solution, this is what we did in our first version of the paper, is remove them. Just take them out, okay? That's an extinct generation estimator, and that works just fine. You've gotten rid of the matching error, okay, because you've conditioned, you just said nobody can live to 115, so if I see you, I can identify the matching errors. You've got to let it go. The problem comes about when you want to estimate mortality models that are earlier in life, where you match someone and the oldest they could be is 85, so you actually think there are censored spells. Okay, that's where what to do becomes a lot more difficult, which you can't say for sure. Yes.
There is another problem in doing that, is that if you're looking at specific groups, because when you're doing that, you're assuming that the probability of dying of the people who are not in the sample, who were removed, are the same as the people in the sample. And so you're biasing your estimates, because if you have a much larger differential in reporting between, let's say, Hispanic and white, and then you do your extend cohort method, then you're going to exclude all of the people who, for whom you don't have information, so might be different.
I think that's right, that's right. So this is under a missing at random assumption. I think that's right, okay? And I actually think, I'm not going to present it here today, there's a lot of reason to think there's not missing at random. So for example, I'll talk about this in one moment, but I don't have a slide on it. One of the things that we have in the NLS is we have a survey report of whether people died. It's very, very accurate, because the Census Bureau is not going to let you not answer the survey. So you show up to someone's door, the relative says they're dead, they said, show me some proof. Okay? They hound you until they know that you are in fact dead. Okay. So for those people, so we have an age of death reported from the survey, right? And then we can find their, and so we go to look at their death certificates. The people that are not matched tend to die very young, okay? And so part of the story, we think, although I'm not going to be able to talk about it all today, part of the story is that the vital statistics registries have been getting better. And if you die young, you die in earlier years when the data was weaker. Okay, so I think it's almost certain, I'm going to estimate a model which assumes matching at random, but it's almost certainly not true. So that's just one example. Okay, so I'm going to skip the simulation, because why simulate when you have real data? So, okay, let me tell you a little bit about the NLS, about the old men cohort. We were interested in an extinct generation, and so we went back, and even this generation is not quite extinct. We went back. I hope none of you were in this generation. I just thought about this. So it's a sample of men. This is the precursor to the NLS-Y. It was a sample of men that were 45 to 59 years old in 1966. There's a comparable sample of women that were 30 to 44. We've matched that data as well. These men were followed until 1990. That's the last time the Census Bureau interviewed them, and they got proxy respondents for men who had died. Okay. And in 1990, and I'll show you this in a minute, in 1990 they matched the National Death Index. And this was what about a little bit over half the men had died by 1990. So we were interested in trying to get almost the complete generation. So we went back to the Census Bureau. We matched in the 2009 National Death Index and the 2012 Social Security Death Index. The 2008 NDI was the most recent one they had. Unfortunately, we would have liked a few more years, but there's some technical reasons. Now, in fact, they do have a more recent NDI. This data is extremely high quality. I think it's better than the NHIS, and it's better because we spent a lot of money doing the match. I mean, that's basically what it came down to, is that we have algorithms that could do the vast majority of the matches went very, very quickly, but for the cases where we did not have a unique match, we then had a lot of data nonetheless that we could go through by hand and match people. And the sample oversamples blacks, which is good, but because of the history, that the sample was drawn in 1966, there's really not a lot of Hispanics in the data. How am I doing? I'm not doing very well on time. Okay, I'm going to jump to some stuff in a minute. Here's the distribution of deaths by source of report. So we actually have 4 different death reports. Okay, we have one that was recorded in the survey. We have one that was recorded in 1990 when they matched to the NDI. We have our match to the 2008 NDI, and we have a match to the Social Security death records. What I want you to see is that not all these things are the same. Okay, in the following sense, the survey match and the vital statistics match are actually relatively close. Okay, but so I should be careful. This is conditioned on someone having died by 1990, so that we have 4 reports. Okay, so these are of the 5,000 men, about 2,700 have died by 1990. Okay, and so for example, if you look at non-Hispanic whites, the survey says 1,730 people are dead. Our new match says 1,797 people are dead, and our old match using the same data said 300 people were less were dead, and that's not because the vital statistics have improved. It's because our matching technology has improved. Okay, that's why we're getting higher matches for the 08 data than for the 1990 data. And then the Social Security Death Index is actually known to be somewhat incomplete, and in fact, you get fewer deaths there as well. I'm going to have to speed up a bit. I have 10 minutes, right? I'm going to skip a bunch of stuff because I want to talk about this is all NLS data, and this is just showing you that if you plot the mortality rates, you get the black-white crossover. So all that you're seeing here is you're seeing that the non-Hispanic white hazard rate becomes higher than the black hazard rate at about age 77. Okay. And I'm not going to do simulations. Okay. So I'm going to do some estimation because I only have 10 minutes from 2 different data sources. Okay. I'm going to look. I'm going to skip right to this. I'm going to skip to these parametric models. Okay, I'm going to estimate some parametric models, and I'm going to do it on 2 different data sources. I'm going to pick the same cohort that's in the NLS. I'm going to show you some. I'll show you some models of hazard mortality models from the NLS cohort, and then I'm going to show you some models from the National Health Interview Survey for the same cohort. So I'm going to define my cohort as people that are born between 1907 and 1914. And what I want to show you is I want to show you a couple things. Okay. One is I want to show you that we can write down a very, very simple measurement error model, okay, which will match the extinct generation model. Okay. Even if you, so the point is what am I going to do? I'm going to show you what happens when you don't do anything. Okay. Then I'm going to show you what happens when you remove the people who are extinct. And then what I want to show you is that this very, very simple measurement error model can replicate the extinct generation when the generation is extinct. Then what I want to do is to go to a model where people are near extinct, okay, so that there's some scope for that you, in fact, wouldn't want to use the extinct generation model. Okay? And what I'm going to show you is that you basically can undo all 3 of the controversies. So that's where I'm going. And as I told Josh earlier, this is a proof of concept. I'm not saying that this is the best measurement model in the world. In fact, I think it is not. But all of this is meant to show is that a very simple measurement error model can get you a very, very long way. Okay? So here's how this model is going to work. I'm trying to make this as simple as possible. So I'm following Allison's 1982 suggestion, which is set up a discrete time hazard model by stacking the data up and removing people when they die, okay? And estimate a logit. Okay, so it's about as simple as it can be. I'm going to be flexible about age, so I'm going to let age go. I'm going to let age affect the hazard rate in a polynomial fashion, and then I'm just going to test down. Okay, so I'm going to see if a log likelihood test whether I can reject more complicated models in favor of simple models. Okay? And then the only thing I'm going to do here is I'm just going to take the traditional logit setup and I'm going to modify it so to take into account matching error. And I'm going to show you, I'm going to do this in the simplest way I possibly can do. And then I'm going to see if I can replicate the extinct generation estimator with this matching model. Okay, so here's the way this extremely simple measurement error model is going to work. There's some fraction of the population, alpha, that has missing records. So 1 minus alpha of the population who die, plus. So you'll have some fraction of the population that are just following the regular hazard process. Okay, and then you're going to have alpha of the censored observation. These are people who end the survey where we don't observe a death. Those are people who have died but their records are missing. Okay? So all I'm going to do here, and this looks ugly, but it's really not ugly at all. I mean, it's not ugly. Okay? The reason I say it's not ugly is this thing right here in the middle, this is the logit function. That's all it is. Okay? And so, in fact, really what's going on is this part here, and this part here is just Allison's logit function. That's all it is. Okay? So all I've done is I split the likelihood function up into censored observations and non-censored observations. Okay? And so it's not, in sense, so we know what to do with the censored observation. I mean, we know what to do with the non-censored observations. Those people died, they follow the logit model. Okay? And all I'm doing here is I'm splitting up the censored observations into these are the censored observations. Okay? So these people here actually survived till the end of the survey. They're true survivors, and they're the 1 minus alpha of the population that don't have missing data. The reason they don't have death records is they haven't died. Okay? Then we have This is the fraction of people who actually survived to the end of the sample. So these are the fraction of people who died. And alpha of them are, in fact, missing. Okay, that's the reason that they're censored, is they're, in fact, missing. Okay? So this is about the simplest measurement error model you can estimate. And all I'm going to do is I'm going to estimate alpha along with the parameters of the hazard function. That's all I'm going to do. Okay? I've already told you about this data. Here's a few facts to show you that this is in fact an extinct generation. What I'm going to tell you is that 2.99% of whites and 3.4% of blacks are censored in this data. Okay, 11.2% of whites and 19.1% of blacks are censored in the 2012 SSDI. They're censored because there are more missing records. Okay. And then I'm going to draw this comparable cohort from the LS. Okay, and the only thing I want you to look at here is that I just told you that 2.9% of records are censored. 2.9% of white records are censored. And when we estimate the fraction of people who, in fact, had missing death records, we get 2.81%. Okay, so we replicate.
Could you just give us some intuition? Where is the identification of this alpha coming from? Is it because you have a quadratic on age and the data is not truly quadratic?
No, it's simply coming from the fact that you have a parametric model on the hazard function. It's just you know what it's just a mixed logit model.
So the parametric model is that the logit is quadratic?
Yeah, it's quadratic in this case. But it's identified.
But if I chose another parameterization, I would get a different estimate?
I actually think it's non-parametrically identified. I think as long as you're willing to make a restriction on if you believe that alpha is not a function of anything, you could be non-parametric entirely on the hazard function. I'm pretty sure. Okay. So all I want you to look at here is that these estimates here of the fraction of people who are missing are extremely close to the fraction that are censored, and that should be true because I've picked a generation that should be extinct. Okay. All right. So now let me confirm the mixture model using the old method. So here's how the hazard model looks. Everything else is pictures, and we'll go fast. So I'm going to show you 3 mortality models, and this is using the NDI death records. Okay, so this is the way Allison's logit model looks, and you can see upward sloping mortality with age. Now what I'm going to do is I'm going to remove the people who are censored, because I think this is the extinct generation, and that is how the hazard model looks. Okay. So now what I'm going to do is I'm going to put them back in. I'm going to put the people I just threw out back in the data, and I'm going to estimate the model that lets me recover the degree of missing data, and that's the model. It almost lies right on top of the. And so this is a very, very simple data, very, very simple measurement model. If we do this for the SSDI data, you can sort of see that this model never. The hazard rate almost never goes up, and the reason is you have 15% of the data is missing, right? So that's what's causing this to come down. Is you got all these people that have 0 probability of dying. Okay, so this is the extinct generation, and unfortunately you can't even see the green, and this just lays right on top of the extinct generation. So this very simple model seems to be able to replicate the extinct generation estimator when there's an extinct generation. Okay. Now, of course, the problem is we often want to estimate models where there's not an extinct generation. So what I'm going to do now is I'm going to take this model and I'm going to move it to what I'm going to call an almost extinct generation. Okay, what I mean by almost extinct is I'm going to use the same cohort, but because of the nature of the NHIS data is that I can't start preserving people until 1986, it means that we have the same cohort, but we know that they've lived 20 years longer. Okay, so the probability of living to age 94 when you know someone was 52, you might believe that the chances of that happening are pretty small, but the chances of someone living to 94 when you knew they lived to 72, that's higher. Okay, so that's the sense in which the generation, even though it's the same cohort, the generation is going to not quite be extinct. Okay, so now, what you can see in this column here is that when we estimate this model, and I'll show you what it does in a minute, we get about 3.4% of whites have missing records, 7% of blacks have missing records, and about 9% of Hispanics have missing, 10% of Hispanics have, I'm sorry, 8%, 3.4, 3.7% of whites, 7.0% of blacks, and 10.8% of Hispanics. This is the Hispanic number, the black number, and the white number. And those numbers are lower than the fraction censored. Why? Because some of the people who are censored are in fact still alive. Okay, so let me show you how the black-white crossover looks. So this is the logit model. Okay, this is that if you just ran Allison's model. That's how the white hazard looks with age. And that's the black, how the black hazard looks with age. So that's the black-white crossover that we've seen many, many times, including in this data set. So all I'm going to do now is estimate exactly the same model, except I'm going to put alpha in. That's really all I'm doing. I'm just taking that likelihood function and allowing there to be this missing data process. So that's how whites look, and that's how blacks look. Okay, so what you can see is that, and you can see two things. Both points I've made before. First of all, the black hazard rate is higher than the white hazard rate at all ages now. Okay, and also notice the variance is bigger. Right, that's the other thing that's happening with this model. The variance is bigger because the model is adjusting for the fact that you don't actually have any data. Okay, so there, you certainly can't. You certainly no. You can see. Okay, so now let me look at the Hispanic, what we call the Hispanic paradox. Remember what we've seen in data before is that the mortality rates for Hispanics are surprisingly low, given low SES. This is the white mortality hazard curve, and that's the Hispanic mortality curve, and that's kind of how you've seen this before. It's lower at most ages than for, there's lower mortality for Hispanics than whites when you just don't adjust for this matching error. And so now I'm going to adjust for the matching error. This is the hazard rate for whites, and that's the hazard rate for Hispanics. Okay. So you can see that there's no evidence that it's lower.
In this model, do you estimate separate age coefficients in your logit for the two different groups? Is it fully interacted?
Yeah. So here's one thing I should tell you though, Josh, is that when you test down, you can't project linearity when you start at age 72, which is a little bit of evidence that there doesn't appear to be much of a mortality slowdown either. Now as this is a logit model, right? So the probability is going to be the coefficient times p times 1 minus p. As long as p and 1 minus p is less than 0.5, the linearity suggests that mortality is just rising with age. Okay. All right. So I'm done. Match data is great, but it's not perfect. And I think we can do a little bit better with modeling, and doing better with modeling, the error process is going to help us understand the mortality process too.
Jump in with questions, please, right away. We're a little bit late.
Well, very, very nice, really interesting. Just to pick up on the last bit, if, for example, Hispanics truly have longer life expectancy by maybe 4 years or whatever it is now in the data, then by 92, which is what, that's the age, that's the end of the observation age, it's going to be it's going to be farther from 0 in terms of extinction than it will be for whites. And so I don't know whether that is a problem in your logit model, but it may be a problem in your add them back in or take them out model. You see what I mean?
So the logit model would allow So the way you would pick this up is you're going to be able to count the number of censored observations. All you're trying to do is to figure out the fraction of them that are really censored and the fraction that are just missing data. So since we allow the process to differ by ethnic group, we definitely can get different rates of missing data for different ethnic groups. Okay. I don't think this is right, and the reason I don't think this is right is that if you take the NHIS data, which is big enough to look at Hispanics, you look at people who are 85 in 1984, and you run them out to 2012, which is, I can't do math, but a lot of years. Okay? Those people are 115, and you have a lot of Hispanics that are, quote, still alive.
Yeah, okay, well, that's more
I don't.
convincing.
What's that?
I said that's more convincing.
Yeah, exactly. So I don't think it's just that they're living longer, and so you're farther from extinction.
The other thought is that you look at Croulet by Louis Henry and whoever co-author is, and he worried a lot about these kinds of issues in parish reconstitution studies because of the high out-migration and people coming back, and he had a number of different estimates. And there might be some useful
I don't know this
insights in there.
literature, so I appreciate it. Ron, I don't know it. Yeah, I'll get some sites from you.
Yeah.
I just don't know this literature. Thank you.
Okay, we're entering the question without answer phase, but.
I hope I have an answer. I'd like to know more about the second mention. You give me the social security database.
I have trouble
The
here.
social security, so you match to the NDI and the SSDI, and I don't know much about the SSDI. Can you
Okay.
tell us more?
Sure, absolutely. So most people know about the NDI. Social Security keeps a death registry as well. That death registry is kept for the purposes of cutting off Social Security benefits when you die. Okay. So the issue there is that not everybody qualifies for Social Security, so not everybody is in the Social Security death index.
Do you know the proportion of the US population?
It's high. It's like 93%. But what
It's
that?
biased,
What's that?
but it's very selective.
Yes. Yes. I mean, it's becoming less selective over time. In the early part of the 20th century, it was very selective.
Public sector in California, so.
Yeah, and also agricultural workers, I think, are not in there. So there's lots of sectors. So, somewhere between 7 and 10% of the population is not in there at all, and then there are matching problems on top of that. So that's why you're getting these rates of missing data that are up between 11 and 19%. Part of it is that whites tend to be in there more than blacks tend to be in there. It's all what you would think. The people have used the SSDI quite a bit because it's free. It used to be online, and you could just go look someone up. And so you don't get causes of death, but you get dates of death. And so for many purposes, we did it because it was free. I mean, we thought it would be good to have another confirmation of mortality. But I think it's well known that it's not as accurate as the NDI. Yes.
Yeah, so this, I may just have missed this, but could you just give me a sort of more intuitive feel of how you get these estimates of the alpha? There's a whole bunch of people, you don't have death records, so as far as you know, they could be alive or they could be dead.
Yeah, so I think,
How do you get?
yeah, so I have to come up with a good intuitive explanation, but let me try, okay? So basically what's going on is, think about if you just had a hazard rate, like constant hazard rate, okay, so at 10%, okay? And suppose you had 10 years of data, right? You would know from that, if it were a constant hazard rate, the fraction of the sample that should have survived, okay? What alpha is doing is it's saying how many more people have survived than the model would say should have survived. So that's where the identification is coming from. No?
So in that case, wouldn't we just get a different level? Or we would get the hazard is changing over time instead of constant?
No, so in other words, it's inferred from the model, as opposed to a whole different strategy is to try to get some empirical estimate. So from my sort of rough idea, you would say, well, let's use successive efforts to try to track these people down. And then we, as these efforts peter out, we get sort of closer and closer to an asymptote of what the true survival rate is of these unidentified, otherwise unidentified people, and then we infer what, you know, the total rate of survival of unidentified people are. That is, you know, my intuition would be to extract it from some kind of empirical process, but if I ever say it's really extracted from a set of assumptions about what the model should look like.
Yeah, absolutely. So the alpha is a function of the hazard model, right? If you change the hazard model, you're going to change alpha sum. Because at the end of the day, the hazard model is telling you how many, you know, at the end of the day what's happening is the hazard model is telling you how many people, how many deaths should have accumulated by now, how many do I have, right? And so alpha is making it so that they match.
So when you compare across groups, and you have reason to believe that the hazard is different for different groups, then you've got to pick a different number.
Yeah, but we can let the hazard, we do let the hazard be different for different groups. Like, you mean blacks and whites, for example.
Yeah.
So the parameters are not the same for.
But aren't those assumed numbers themselves generated some assumption based on what is originally a missing data problem?
Can just repeat that. I mean,
I don't think he understood what you did when you took the certain generation that you thought had all died. The extinct generation said, okay, there's actually 2.5% of these guys still left,
yeah.
according to the
Okay,
records.
maybe that's
And that's an estimate that is non-parametric. And then you estimate the
Yeah,
model
exactly.
to 6%.
Exactly. So that, yeah, thanks. Dave.
okay.
So-
So maybe that's the lost generation thing. Maybe you are wrong.
Yeah, but that, I mean, that's one place we can test it, because we really believe that when people are censored at age 106, that they're really not alive, that they're really missing. I mean,
So all missing cases there, 100% of them are dead.
that's, yeah, and our model suggests that that's true.
And how many years back do you go on that? So you say everybody at 110 is dead?
Well, I think if you start people at, what it turns out empirically, is that if you start people at age 52, going up to about 97 is enough for everyone to be dead. But if you start people at 72, you have to go farther.
All right.
Okay, thank you very much, Seth.